Well, hey guys, I thought I would stop in and share one of my favorite math problems with you and sort of how to solve this one. This was a problem that appeared in a math competition back in 2004, sort of a high school math competition. But it's actually quite an intricate problem, and it involves a lot of different mathematical ideas. So I especially like it, and I wanted to share the solution with you here. The fundamental question is, how many 1,000 pointed stars can you draw? How many are there? How many different such stars can you draw? And of course we have to agree about what a star is. The basic idea is that it's a union of a bunch of line segments. Those line segments must intersect one another. You can't just draw, a bunch of segments around the edge of for example here, you can't just draw a pentagon or a hexagon or anything like that. The lines have to intersect, they have to cross. They have to all be the same length, and they have to all turn at the same angle as you look at the picture. So, you can play around with a problem like this by starting with some much smaller numbers of points. So instead of 1,000 pointed stars, we could look at our classic example that everybody knows, which is a star that has 5 points. And the way I'm going to help myself visualize these is I'm going to put the points equally spaced around the edge of a circle. So here I've got 5 points around a circle. The idea is that to draw my star, I have to start connecting those points. If I connect these 2 points here, notice that I've skipped 1 point in between, right? I'm connecting really every second point around this circle. And you have to consistently do that. I know my picture is not perfectly to scale. You have to consistently, once you decide that you're going to connect every second point, which is what I did right here, then you have to continue in that same manner, because remember, all of the line segments have to be the same length, and they have to turn at the same angle relative to one another. So this is an example of a 5-pointed star, and it's actually the only one that you can draw. So I'm connecting every second point here. I'm going to write j equals 2 to remind myself of that. Okay? I'm connecting every second point. Of course, if I imagine connecting the segments in the reverse direction, so in other words, if I think about starting at this point right here, this is the first point, and I make this the second point, then I've actually connected, if I still imagine the clockwise orientation, I'm actually connecting every third point. Okay, so this would be 3, and then this would be 4, and then this would be 5, right? So you could actually associate 2 different j values. J, again, I'm just keeping track of how many points I'm skipping, basically. So j is I'm connecting every jth point. So either every second point if I want to trace this thing out clockwise, or every third point if I want to trace the figure out in a counterclockwise manner. Okay? If I take, let's say, 6 points, right, and I think about what j values could I use. By the way, notice you can never use j equal to 1. If you connect every first point, in other words, if you connect every point, you don't get a star because none of the segments cross, right? So j cannot be 1, and therefore it also cannot be 5, because j equals 1 would be connecting every first point clockwise, whereas j equals 5 would connect every first point counterclockwise. All right? So what about connecting every second point? Well, if we connect every second point, you see that we form a premature triangle. Now, this is also not allowed in a star. We have to actually hit every single point before we return back to the first point. That's really also part of the definition that I should give you. So j equals 2 does not work either, and neither does j equals 3. J equals 3, you're going to bounce across the diameter of the circle and head right back to the point you started at way too soon. Okay? So actually there are no stars that you can draw with 6 points. Okay? Let's talk about 7 points. Again, j equals 1 and j equals 6 will create a septagon, which is not an acceptable star. If we take j equal to 2, let's say we connect every second point. Let's see if that works. It looks like we're going to trace out the whole star here, right? So this would correspond to j equals 2 or j equals 5 if I connect the points in the reverse direction. It's the same star. This is only one star, but there are two different j values that produce that one star. Okay? Now, on the other hand, I can also, let me draw my 7 points again, because it turns out, see if I can get this about right, turns out we can also get a star by connecting every third point. So this is going to be j equals 3. This is not the same star. It's going to look a little different. Okay? So there's a star. It's not equivalent to the star that I drew up here. This one corresponds to j equals 3 or 4. All right? The idea here is to look for a pattern, sort of see what's going on. If we take n equal to 8, right? If you obviously you cannot let j equal 1 or 7. If you let j equal 2 and you connect every second point, you're going to make a premature square, right? You're not going to get a whole figure. So j equals 2 and j equals 6, we have to throw those out. If we connect every third point, now we're going to get somewhere. Okay, we're going to get this star right here. Okay, so there is a star. That corresponds to j equals 3 or 5. J equals 4, however, does not give us a star. It just connects, again, across the diameter of the circle. What I hope you're noticing about the j values that work is that they have no common factors with n. If you took the, so it's actually a little bit of number theory. If you took the factorization of n and you look at which j values give you full stars that you're looking for, those j values are exactly those values that are relatively prime to n. No common factors with n, right? So, for example, if n was equal to 9, we could have a star with j equal to 2 or 7, and we could have another star with j equal to 4 or 5. But 3 and 6 wouldn't work. 3 and 6 have common factors with 9, so you would create premature stars that way. And of course, 1 and 8 we have to throw out because that would just give us, again, an n-gon, a 9-gon, I guess, in this case. So I hope this is giving us the idea of how we can find the number of 1,000 pointed stars. We're certainly not going to draw them all, but we need to figure out how many numbers are relatively prime to n. And there's actually a function for that. It's called phi of n. This is it's really the size of the set of k, where k is between 1 and n, and the greatest common divisor of k with n is equal to 1. And this is the set whose size we're looking at. Okay. So what we're going to do is we're going to find the size of that set. So the number of n pointed stars. Here's the answer, guys. For any n, I can tell you how many stars there are. You're going to take how many values are relatively prime to n, how many integers between 1 and n are relatively prime to n. You're going to subtract 2 because remember that, well, 1 and n minus 1, those are going to be in this set, right? The number 1 has no common factors with n, and n minus 1 has no common factors with n. But those two values of j do not give us acceptable stars. They give us n-gons. So we're throwing those out here. So what we have here is the number of j values that actually produce legitimate stars. But we have to take half of that many, right? Because remember that for every value of j that we find, there's another value of j that traces that star in the opposite order. Okay? So really, to find the number of 1,000 pointed stars, what I really need to try to figure out here is what is phi of 1,000. This is the phi function, okay, the Euler Key Function. How many numbers are relatively prime to 1,000 that are between 1 and 1,000? Okay. So we actually have to think of that in terms of a little bit of a number theory concept here. So 1,000, if you think about it, is just 2 cubed times 5 cubed. Any number that has factors of 2 or 5 in it will not be relatively prime to 1,000. So what I'm going to do is I'm going to take all 1,000 numbers between 1 and 1,000, and I'm going to subtract the ones that are not relatively prime to 1,000. Well, that would be those numbers that have factors of either 2 or 5 or both. I think you would all agree that, well, a number that has a factor of 2 in it is just an even number. And out of these 1,000 numbers between 1 and 1,000, exactly 500 of those would be even. So I'm going to subtract those. Let me just kind of group together everything I'm going to subtract. So we have 500 even numbers. How many numbers have factors of 5 in them? Well, that would be every fifth number. 5, 10, 15, 20, and so on. Well, there would be 200 of those between 1 and 1,000. So we're going to take those out as well. It turns out, though, we've inadvertently taken out some numbers twice now. We've taken, in these two collections, we've taken out the even numbers and the multiples of 5. But if a number is even and it's a multiple of 5, then it's actually also a multiple of 10. Any number that is a multiple of 10 was taken out here because it would be even, and it was taken out here because it's also a multiple of 5. Well, we don't want to take it out twice. So to make sure we've only taken out the multiples of 10 once, I'm going to subtract 100 from the numbers that I'm removing. Okay? So I remove 500 numbers, I remove 200 more numbers, and then I realize that I double removed some of them. So I'm going to stop double removing them by subtracting that value right there. This turns out to be 1,000 minus, what is this, 1,000 minus 600, which is 400. So how many 1,000 pointed stars are there? 400 minus 2 over 2. So the answer here, just put the answer. 398 over 2, which is 199. So now you know how many n pointed stars there are for any value of n. Here's the general formula, and here's the answer for n equals 1,000. I hope you enjoyed the little presentation. There's a little bit of drawing the pictures. Then there's the number theory. There's the counting argument. This is what I like about the problem. There's a lot of different things going on that we can explore. Hope you enjoyed it. Thank you very much for your attention.